If our goal was to send a manned crew to Mars, what kind of effect would this have on the astronauts? Dr. Gene Sabanga will talk to us about what might be some effects of long-term space missions.
Well, over the past 10-15 years, we've been applying a clinical diagnostic test for evaluating osteoporosis in our astronauts, and some of that data has revealed that we have some very unique changes in our astronauts up in space.
Such as?
Well, they have a very accelerated rate of bone loss, and the bone loss is not general across the skeleton, but it's actually at specific sites. It's the weight-bearing sites that we have here on Earth. It's the lower half of our body versus the upper body. It's our hips. It's our spine.
Let's take a deeper look at how space exploration affects astronauts' bones.
The bones of the human skeleton provide structure and movement by acting as levers for the attachment of muscles. Over time, bones change size, shape, and density as a result of the changing pressure and weight, or load, put on the bones through physical activity and gravity. The primary load-bearing bones are the long bones of the legs, pelvis, and lower part of the spine. These contain trabecular bone, a microscopic, lightweight, yet very strong bone that, like a bridge structure, can support large loads. Our bones are adapted to the amount of gravity we experience on Earth. In the reduced gravity of space, the body detects less load to bear and begins to thin what appears to be surplus bone structure. The result is bone loss. This happens quickly, especially in trabecular bone. On Earth, a woman over 50 who is untreated for bone loss can lose 2% of hip bone mass in 1 year. In space, astronauts can lose the same amount in a single month. Upon returning to Earth, regenerating bone mass can take 3 times as long as it took to lose. NASA research has identified resistive exercise, like lifting or moving a weight, as an effective way to minimize bone loss on Earth and in space. Astronauts on the International Space Station perform up to 2.5 hours of exercise 6 days a week to minimize the negative effects of spaceflight on their bones and muscles. NASA's research into bone loss has helped to heighten our awareness of the connection between gravity, activity, and ways the body gets signals for the...
So let's compare data from the International Space Station with the IRED machine versus the Russian space station Mir with the treadmill and bike that we see that them use, the two different populations that we have. So let's take a look at the data for the bone density loss. Looking at the treadmill and bike, we see that we actually have some larger values, some more negative numbers than we have for the IRED. So we see there's more bone density loss happening in the treadmill and bike group than with the IRED group. And let's take a look at the graph here. When we see this, we see that the shape of the IRED is skewed to the left, while the treadmill and bike is actually skewed to the right. We see that the IRED has a higher median than the treadmill and bike, showing that we have less bone density loss happening, and by quite a bit. I mean, we see that the first quartile of this is at the third quartile of the treadmill and bike, and we can see in the means as well that we also have a significant difference. But is it enough to say that one is better than the other? And that's what we want to take a look at. So let's do a hypothesis test that alpha is 0.05. So our null hypothesis would be that the two are the exact same. Or if we moved it around, the mean of the IRED minus the mean of the treadmill and bike would be equal to 0. On average, using the IRED exercise device is the same as using the treadmill and bicycle in mitigating bone loss. Our alternative would be that the IRED is better than the treadmill and bike. Or if we subtract them, that the difference would be greater than 0 because this would be larger. On average, using the IRED device is better than using the treadmill. Okay, so here's our assumption. By assuming that the null hypothesis is true, we're saying that there's no difference between the treadmill bike and the IRED on bone density loss. Because of this assumption, the only reason we got a difference in the mean BDL of 0.052 was by pure chance. In other words, the people that got assigned to the treadmill and bike would have lost that bone loss no matter what treatment group. So our difference came from the random assignment of treatments, or the shuffle of the deck. So how can we test it? Let's reshuffle the deck. Each time we'll shuffle the deck and redeal our treatments. Then we'll calculate the difference in the mean of the IRED versus the treadmill and bike. Our assumption says that each person would lose their bone density regardless of the group. So we'll see how often do we get a difference of 0.052 or greater by pure chance. If this value happens a lot, that would give us a large p-value. We won't be able to say one is better than the other because our assumption could be true. If it happens very little, we could reject that null hypothesis, say we have a difference in the treatment. Okay, everyone, so the idea is that we are assuming that there is no difference between the treadmill and the bike and the iRed. So, person number 5, for instance, would have had a bone loss of 0.067, regardless of whether he was in the treadmill and bike or in the iRed group, and same thing with person 14. So, what we're going to do is we're going to reshuffle the group, so now notice person number 5 has now been assigned to the iRed group. Okay, we're going to reshuffle this. I'm going to calculate the mean of all the iReds and the mean of the treadmill and bikes. And we're going to find the difference between those two. So here's what I'm going to do. I'm going to collect it. So there we go. There's the first one. And that would be negative 0.019 because we're in the thousandths. And I'm going to do it again. Notice that each group changes and we get a different value. We're reshuffling that deck. Reshuffle, reshuffle. Okay, so it's good to do this one time, but let's go ahead and do this 1,000 times and see what happens. Alright, so each dot represents a reshuffle and a difference in the means. And as this is building up, we want to see how often do we get a value of 0.052, which would be 50 or greater. And what do you actually notice in this case? It never happens. So what that tells us is that if there was no difference in the treatments, I would get a sample this extreme or more by pure chance never out of 1,000 times. So what that means is since that's so unlikely to happen by chance, there's probably a difference in the treatments that we have. So our grand conclusion, because our p-value is less than 0.05, we reject the null hypothesis. We have statistically significant evidence that iRed reduces the bone density loss better than the treadmill and the bike. Okay everyone, so we're going to run a 2-sample t-test for the means. So I've calculated our x bar 1, x bar 2, standard deviation, and here's our formula. Notice we're taking the difference of the samples minus the parameters just like normal, divided by the standard deviation of statistics. And if you notice this, what we've done here is really added their variances together. Since I'm using a sample value, I'm using the t-distribution. Now degrees of freedom get a little tricky. I'm going to save you from the formula. If you need to, just use the calculator to grab it out. It'll tell you every time when you run the test. And really for these ones, I'm not going to make you write the formula. You can just use the calculator. Or what you can choose to use is the smaller of the two sample sizes minus 1. So whichever smaller degrees of freedom makes it more conservative. So here's our null and alternative hypothesis, just like we had previous on the slide, and our conditions. Both must be random samples, or we must randomly assign them to the treatments. The two populations need to be independent of each other, and then what we need is, with the shape of these distributions, since we're in the T, we need to make sure that they're skewed with no outliers, although at 24 that's pretty big, but both distributions are skewed, and I would show the graphs here, but I showed that on a previous slide so you can see that. Alright, so here's our test statistic. T equals, and I need to grab my degrees of freedom. So for right now, let's just put the smaller 2. So my degrees of freedom would equal 11 because of the smaller 2 sample sizes. Plugged in my values, difference of the statistics, minus 0. Now you might ask, why is it 0? Well, because our null hypothesis says that they're the exact same. So therefore, we plug in 0 in those values. There shouldn't be a difference there, divided by what we have here. So now I go to the test. I run in the calculator. I go menu, statistics, stat test, and a 2-sample t-test. I put in list 1, list 2, and I have my alternative hypothesis. And you might see pooled there. That's something that's talking about the variance. So in this case, we almost always say no. So let's go ahead and hit enter. All right. So here's my values. There's my t-value, 4.48. And I get a p-value of 0.00009. 0.098. And we see that's really small. I should have said my alpha 0.05 we said before. So let's just make our final decision here. 0.000098 is less than 0.05, so we reject HO. We have statistically significant evidence that the mean of the iRed is greater than the mean of the T and B. So therefore, they are losing less bone density. And there is the formal test that we would run, tied in with the other thing.